Okay, thank you, Peter. So I want to thank the organizers for having invited me here to this very nice conference in Boston. I also want to thank my collaborators of what I will tell you about. And I will tell you about our latest results on quantum simulation in the context of dynamical gauge theories in Peter Soller's group. So quantum simulation in the last years has been mainly focused on condensed matter problems or spin models, in that we want to emulate the Bose-Hubbard Hamiltonian or spin models such as Ising interactions, and a variety of systems such as cold atoms, trap ions, quantum dots, superconducting qubits, and photonic devices have been proposed for this purpose in both analog and digital approaches. And it is remarkable that current experiments are already addressing the boundaries that other methods such as Monte Carlo or DMRG cannot address, and particularly interesting are the cases in which we have time-dependent problems due to the exponential growth of computational time. So it is natural to ask ourselves what is next? What is now we can address this type of problems, where should we go? So a possible answer to this question is the simulation of gauge theories, and two paradigmatic examples in this context are the theory of quantum chromodynamics and spin liquids, which may be relevant for explaining high temperature superconductivity. And there are many unknowns in this context. For example, the phase diagram of quantum chromodynamics has only been proved in a very specific region, so there are many unknowns in this phase diagram. Likewise, spin liquids, although have been simulated using Monte Carlo, there are many open questions. And it is not worth it that the standard model itself of particle physics, it is formulated according to two basic requirements. The first one is Lorentz covariance, and the second one is gauge invariance. So what is, this is the outline of my talk. First I will introduce you to gauge invariance and lattice gauge theory. Then I will present the so-called quantum link models to simulate these kind of theories. Then I will give you the probably simplest non-trivial example of a gauge theory, that is the SCHWINGER model, which is quantum electrodynamics in 1+1 dimensions. Then I will explain how to realize such a model with trap ions and give you a little bit of an introduction of how to do that with superconducting circuits. And finally, I will end up explaining how to implement certain constraints that these gauge invariant theories are subject to, not by only a Hamiltonian manner, but by also via dissipation. And I will end up giving future perspectives. So what is gauge theory? So if I go to Wikipedia, I read in physics, gauge invariance, also called gauge symmetry, is the property of a field theory in which different configurations of the underlying fields, which are not themselves directly observable, result in identical observable quantities. A theory with such a property is called gauge theory. A transformation from one such field configuration to another is called gauge transformation. So if I continue reading, I see this article may contain parts that are misleading. This article needs the attention from an expert in physics. So let's see if we can do better than that. So gauge theories emerge from the requirement that the Lagrangian or the Hamiltonian remains invariant under a local transformation of this type, in which my matter fields, typically fermionic matter fields, undercome a local transformation of this type. And for example, I take here the Lagrangian of quantum electrodynamics, needs to remain invariant under such a local transformation. And I very quickly discover that in order for that to be true, I need to introduce a new degree of freedom in my theory, namely the gauge field, in such a way that the Lagrangian remains invariant. And these are the gauge fields that I will be trying to simulate and that I will be talking about. so the type of interactions that I will be interested in simulate take this form over here. So you can realize that this is somewhat abstract to simulate in a quantum computer. Let's see how we do that. And it is also not worth it to see that this is in contrast to the simulation of static gauge fields in a sense that this field here has its own dynamics, has its own quantum dynamics. So let's see how we can simulate this type of theories here. So when trying to do that, we face two major challenges. The first challenge that we face is that the gauge fields introduced in the previous slide are continuous degrees of freedom, and for a quantum simulation it's simply convenient to move to the framework of lattice gauge theories as formulated by Wilson. And in this framework the space-time is discretized, and my fermionic degrees of freedom live on the vertices of the n-dimensional lattice. And for example, I can take here for this analysis a free theory in which I have a kinetic energy and a mass term. And when going to the lattice formulation, I discovered that the naive kinetic energy that I write down via this spatial derivative takes this form here, and the mass term takes this form. Now a gauge transformation in this discretized space takes this generic form, where omega is an Hermitian operator. And when I perform this gauge transformation in this Lagrangian here, I very quickly realize that the mass term remains invariant because this omega is Hermitian. However, the kinetic energy formulated here is not gauge invariant. And this leads to the emergence of dynamical gauge fields. So Wilson, what he did is to introduce an additional operator in the lattice, in the kinetic energy, in such a way that now when I perform my gauge transformation, it remains invariant, provided that these gauge fields transform in this very particular way. And U is the, in this case, bosonic gauge field. So notice that these gauge fields live on the links of the lattice, since they connect site n, fermion n at site n, and fermion at site plus n plus 1, n plus x. Given these new degrees of freedom of my theory U's, now I can, of course, include additional terms in my Lagrangian, such as the interactions between gauge fields. And one can realize that in order to have gauge invariant objects, a typical interaction takes the form of a product of 4 U operators. So these are the typical Lagrangians that I will be trying to simulate in my quantum simulator. Now it's convenient again to work not with a Lagrangian formalism, but with a Hamiltonian formalism. And when I do that, when I go from the Lagrangian to the Hamiltonian, I encounter again the kinetic energy, which has this sort of assisted hopping form, the mass term. Then I encounter a new term which comes as the canonically conjugate variable to the U operator, as it's usually the case with the momentum when one goes from the Lagrangian to the Hamiltonian formalism, and the interaction between gauge fields. And it turns out that when I go to the continuum and interpret these terms here, so this is the kinetic energy, the mass term as explained before, and these two terms correspond to the electric energy and the magnetic energy of my theory, for example, in quantum electrodynamics. The second challenge that we face when we try to simulate a lattice gauge theory is that the gauge fields, these U operators that I introduced in the previous slide, live in an infinite dimensional Hilbert space. But there's a way around this, and this is to use the language of the so-called quantum link models. And the idea behind this is that because the U's and the E operators fulfill commutation relations that resemble those of an angular momentum algebra, I can actually represent them by spin operators. So without loss of generality, I can write my generic Hamiltonian gauge invariant in this form, in which the kinetic energy now takes the simplest form, in which the assisted hopping from site n plus mu to site n is assisted by a spin flip. And then the interactions between gauge fields now sound more familiar to us because they are just four-body spin interactions. So this is the type of Hamiltonians that we will be trying to simulate. Another remark on gauge invariance is that because, as I explained before, the definition of gauge invariance is that your Hamiltonian remains invariant under a local gauge transformation with certain generators of my symmetry. This immediately implies that the Hamiltonian commutes with these generators of my symmetry. The Hilbert space is divided into different sectors, different gauge invariant sectors, corresponding to different eigenvalues. And in particular, I will be focusing on one of these sectors, which is the gauge invariant sector corresponding, for example, to lambda equal 0. And this constraint is what the high energy physicists call Gauss law. So not only my Hamiltonian needs to be gauge invariant, but I also need my Hilbert space to be fulfilling this requirement. A possible way to do this, starting from a microscopic model that might not be intrinsically gauge invariant, is to impose a very high energy scale in my Hamiltonian, given by u, g squared, in such a way that the ground state of my system corresponds precisely to those states fulfilling this Gauss law, and therefore I am selecting in such a manner the gauge invariant part of the Hilbert space. So let me explain a particular example of a gauge theory, which is quantum electrodynamics in one dimension. And in this case, the magnetic energy introduced previously, which was given by the interactions of these four spin operators, is not present because this is just present in two dimensions. And my Hamiltonian takes this form in which I have a kinetic energy part, a mass term, and the electric field part, which in the context of these quantum link models takes the form of SZ squared. Now, if I want to simulate this with, for example, trapped ions, I can use in one dimension again a Jordan-Wigner transformation in which my fermionic matter fields are represented by spin degrees of freedom. So my new Hamiltonian takes this form, and what I've done is simply mapping a hopping of a spin of a fermionic degree of freedom into a spin operator, a spin flip-flop operation assisted by the spin on the link representing the gauge field. So it's a spin-assisted flip-flop operation. So I will be asking myself, how could we actually realize this type of interactions with different systems such as trapped ions? So this model is interesting because, for example, in the regime in which G is much smaller than the mass and J, as M and J compete, I encountered two different phases as given by this global order parameter, which is the magnetization of the spins on the links. So what I discover is that in the limit in which M divided by J goes to minus infinity, this order parameter actually takes the value 0. However, in the opposite regime, in which M divided by J goes to infinity, this order parameter takes the value of 1. And I can actually interpret these two phases in terms of particle-antiparticle excitations in such a way that I have a one-dimensional lattice, and this phase corresponds to a particle and antiparticle alternating and joined by an electric field flux. The other phase, however, corresponds to an electric field flux biasing my system with no particles in between. And I can again map this into a spin language in which this first scenario corresponds to this sort of a staggered magnetization in the link variables. However, this other regime corresponds to this sort of ferromagnetic order. Another important regime of the Schwinger model comes when I consider a regime in which J is much smaller than the mass and G. And the reason this is interesting is because it predicts physics of quantum chromodynamics. In the following sense, if I have a quark and antiquark in quantum chromodynamics and I start separating them, the energy of the system grows linearly grows linearly with the particle antiparticle distance. This is called confinement. If I continue doing this, at some point the energy of the system of the string in between becomes so large that it is actually favorable for the system to break the string and to create a pair particle-antiparticle forming two mesons, two disconnected mesons in between. So I can actually map this process in which the first state is the string, which connects a particle and antiparticle via a flux line, and the meson state has particle and antiparticle pairs in the form of mesons, but no flux in between. And I can actually map this to the spin language, in which I identify a now local order parameter given by what's the value of the spin, for example, at the link in between. And if it is 1, I will know that I'm in a string phase. However, if it is 0, I will know that I'm in the meson phase. And because these string and meson energies are different, and in particular the string energy grows linearly with the system size, there is actually a transition between string and meson phase. For example, if I fix the size and vary the ratio mass over G, I encounter that as I look at this local now order parameter, it varies from 0 to 1. So how can we realize this type of models with different systems? So let me consider the simplest case in which I focus on a spin 1/2 in such a way that the electric field term is a constant. So this set squared value is just a constant. So now my model is just given by this simpler Hamiltonian over here. So with trap ions, to realize such a model, I will need two different spins alternating. The first spin will correspond to the matter fields with a particular energy splitting. The second spin in between matter fields will have a different energy splitting, and I will try to realize, as I mentioned, a spin-assisted flip-flop between the sigma operators. So this is the first ingredient. The second ingredient, as I explained before, is to remain in the gauge invariant part of my Hilbert space. As I mentioned, this can be done, for example, by imposing a high energy scale in my problem, accompanying the generators of the symmetry squared. And when I look at the generators of this model, actually they take this particular form here. And what this gives me is that I need to engineer interactions of the form sigma set S set or S set S set interactions. To do that, as we have learned in this conference, one can actually use two laser beams, both in the optical domain or in the hyperfine domain. And the price to pay, however, is that these interactions have a long range, typically dipolar decay. However, the interactions needed to ensure gauge invariant are quasi-local. So these interactions set have a term in the Hamiltonian that I want, that gives me the gauge invariant part of the Hilbert space. However, I will be committing an error given by the dipolar decay of the set interactions. The second ingredient that I need to to represent this type of interactions here are, for example, XX interactions together with magnetization term in the link degrees of freedom, in such a way that I could perform perturbation theory on these terms over this big energy scale. And not surprisingly, when I go to second order in perturbation theory, that is, I find a J of the form Kb over U, I encounter, because I will have interactions of the form sigma x Sx sigma x, I will encounter, if I perform things close to resonance, terms of this type. And I will be able to actually neglect terms given by next to nearest neighbor interactions, both because they will be either off-resonant or because they will decay as a dipolar power law, and they have a coupling constant that is sufficiently small. Now the mass term can be simply accounted as a AC Stark shift in my theory. And the term that I cannot neglect, however, is this error term that has a quite large prefactor and does not give me, in principle, what I want, although it is gauge invariant. So this is the result from a simulation that we have done. And the green plot shows the ideal case, the ideal scenario, in which I see the transition of this global in this global magnetization or the parameter. And when we actually consider these error sources, what we see is that we capture well the transition. However, depending on the ratio J over U of my theory, I encountered this second step here, which actually emerges from these long-range set-set interactions. And this ratio of J over V over U, this would be a U, needs to be small in order for perturbation theory to work. However, cannot be too small, because as I increase the U interaction, these long-range set-set interactions start to matter more and more, and this green curve is reproduced worse and worse. Let me now tell you how to bring these ideas to the context of superconducting circuits, in which we have gone a little bit beyond and reproduced this Schwinger model for not only spin 1/2 but also spin 1, and including dissipation. In order to encode the spin 1 in my link variables, what we can use is the so-called Schwinger representation, in which we use two bosons to encode this spin degree of freedom. And this is denoted by these equations here. So now what I have is sites representing my matter fields joined by a link which is composed of two harmonic oscillator variables. And one can see that precisely a microscopic model like this, in which I have local terms, for example, this one will give me this term here. This one will give me this term here, and these ones, when I perform perturbation theory on a James-Cummins coupling with respect to this big energy scale here, actually give me this type of interactions, which I am looking after, which is this correlated hopping. So again, not surprisingly, I am hopping an excitation from site I to site I+1, mediated by these bosons in between. So let me illustrate this. I will initially prepare my system, for example, in which my site I has an excitation. I have an excitation on each resonator, and this, in this language of Schwinger bosons, represents a spin 0. And on site I+1, I have no excitation. So given this initial preparation, because the number of excitations is conserved in my model, I could have a relaxation process here, however, transferring the excitation to this first resonator. But because of this large energy scale U between resonators, what needs to happen actually is that the second resonator relaxes to the ground state, transferring the excitation to the neighboring site. So one could think about a possible simple experiment in which one performs an adiabatic sweep across this transition that I described by transferring an excitation, and in such a way that we actually perform a measurement of the middle spin, this sort of local order parameter. So when I do that, I need to account for dissipation in my system, and this is the result that we find. The red plot is the microscopic model, meaning the ideal scenario. And when I include dissipation, I actually see that the transition is captured quite well for realistic system parameters. So in principle, this has been done only for a building block that is two sides and one link. And what is important is that when I realize such an experiment is that gauge invariant, that is gauge invariance from the microscopic Hamiltonian is fulfilled. That is, if I monitor the value of this G operator, G squared operator, as I go across the transition, it doesn't grow too much. So, for example, for this state-of-the-art parameters, we see that the violation is on the order of a few percent, which is quite reasonable. So let me now tell you about a different way to implement this so-called Gauss law. And this can actually be seen as a quite generic way to implement constraints that we so frequently implement in Hamiltonian dynamics. So we have learned before that we might start from a microscopic model which has a gauge invariant part and a gauge variant contribution. And we need to fulfill a particular constraint. Here it's called Gauss law. And we mentioned that a way to do that is via a very high energy scale in my problem. But interestingly, this can also be done via dissipation in a way that I could engineer jump operators that actually correspond to these generators of my symmetry, in such a way that if kappa dominates the dynamics, that is, if kappa is much larger than the typical energy scale of H1, which is the gauge variant contribution, let's call it lambda, if kappa is much larger than lambda, then I will remain in the gauge invariant part of my Hilbert space, here represented by this part, HP here. And interestingly, this can not only be done via quantum noise, but also via classical noise. If I start with a microscopic Hamiltonian in which I have H0, H1, and then a time-dependent signal which actually accompanies the generators of my symmetry, I can prove that this actually reproduces a master equation of this type, and therefore it will remain gauge invariant. My dynamics will remain gauge invariant for kappa much larger than lambda. So let me give you a particular simple example in which H0 is simply given to 0. H1 is a gauge variant contribution of the form lambda sigma x, and my generators of the symmetry are given by sigma z simply. So what I'm doing here is like I start in a gauge invariant part of my Hilbert space, and the interaction tries to take me out of the Hilbert space. However, when I introduce these noise operators, what I'm doing in a way is to shake this gauge variant of my Hilbert space in such a way that there's never a resonant condition to access these levels here in the gauge variant part of the Hilbert space. And one can actually prove that the probability of staying in the gauge invariant part of the Hilbert space goes exponentially with lambda squared over kappa, which actually goes to 1 when the ratio kappa over lambda is much larger than 1. So this can be seen not only in the context of lattice gauge theories, but also as a generic way to engineer constraints to Hamiltonians via classical noise. And this actually complements the very many already proposals from the latest years on how to realize a lattice gauge theory with cold atoms. Finally, let me give a little bit of a prospect. So once we are there, where can we actually go? So a possible interesting way to go are to study non-trivial models present in condensed matter, such as, for example, the so-called Roxar-Kivelson model, which actually has 4-body spin interactions of this form and a very rich phase diagram with a phase transition and, importantly, at the so-called Roxar-Kivelson point, confined to the confined phase transition. So there's a point in the phase diagram in which the system is deconfined. And we have actually already started to analyze how to realize such interactions in an analog way, which would be very interesting to study open questions not only in phase transitions, but about confinement and about string dynamics in my system. And the idea for that we have thought about with, for example, superconducting circuits is to connect the link variables, which represent the gauge degrees of freedom, with a common mode here given by an harmonic oscillator in such a way that I have an interaction in my Hamiltonian that looks like S plus S minus, that when I perform perturbation theory will give me actually 4-body interactions, S plus S minus, S plus S minus, but also an interaction of the form SZ between nearest neighbors, which is dependent on the, which is coupled to the common bosonic mode. And when I eliminate this bosonic mode in the middle, I will again come up with 4-body spin interactions of this form. So this brings me to my conclusions. I hope I have convinced you that the quantum simulation of lattice gauge theories is interesting. I have in particular analyzed the example of how to implement it with trapped ions, and I have open some questions on how to do that with two-dimensional models, and in particular it will be in the future interesting to study the non-abelian scenario where we'll eventually connect with quantum chromodynamics and address interesting questions open in the literature. So thank you.
So yeah.
Have you thought about implementing in the non-abelian that you mentioned now, the nonlinear gauge parts, like 3-vertex or 3-body vertex or 4-body vertex or things like that?
This has been done in the context of cold atoms. However, we have not done it yet with trapped ions or superconducting circuits. Yeah, it has many degrees of freedom. In particular, people use the so-called reason degrees of freedom. So it's just a question of the fact that you have to encode your degrees of freedom in many internal levels in your trapped ions. So it's just a question of complexity. Yeah.
I have another question. How does the number of ions scale with the number of bosonic excitations that you have in your theory? Because you map the bosons onto spins, and I mean.
So you're talking about.
I mean, when you map onto the S spin, you have a certain number of bosonic excitations.
You're talking about this part here, right?
I mean, in the trapped ion.
In the trapped ion, what we have done so far is basically study the case of a spin 1/2. So this can be simply be represented by a spin 1/2, by spin excitation. So you don't map it into bosons. The way this works actually is, of course, you make use of the bosonic degrees of freedom when you want to sort of engineer this type of interactions in such a way that, of course, this U is an effective U, but this S, it's important that it's just a central spin. Yeah. Yeah.
Okay.
In this dissipative constraint, when you impose the Gauss law, you always end up with the zero eigenvalues, because you have some sort of effacing in a sense, right?
Yeah, this is sort of a dephasing
So
for this form because it's sigma set interaction.
How do you know that you don't end up in some other eigenstate of the G operator?
Well, as long as you are in the gauge invariant part, you are fine.
You have to start from a sector and then you remain there.
Yeah, that's the idea. Yeah.
Okay, Valerie?
On the next transparency, you showed this phase transition basically, and I see two phase transitions. What kind of states do belong to this regions?
That's a good question. Actually, we have not analyzed that, but indeed, there's a double step here, which comes from the long-range interactions. We have not analyzed sort of intrinsically why this happens, but I can tell you that if you actually resolve this model with 4 ions, meaning that you don't have these long-range interactions. Actually, the ideal model resembles very much what you get. So this really comes from the long-range S-set interactions, as far as I can get.
So what are the ion numbers here? Is it?
Sorry?
So what are the ion numbers here for this simulation?
So which numbers specifically?
So how many ions is this?
Okay. This was around 8 ions. Yeah, 8 to 12 ions, I think. And we did it with 4 periodic boundary conditions to ensure that we don't get these long-range interactions, and then you get much better results. However, eventually you want to scale it up, so this is an open question.
Okay, are there any other urgent questions? If not, then let's thank David again.